Hello, everyone. This is Dr. Hopkins narrating the next in our series of videos for 472. And today we're going to mix liquids. We're going to look at the thermodynamics of mixing liquids, in particular volatile liquids that have a vapor pressure. Okay, so we know with a pure liquid, based on our phase changes or phase diagrams, that there is an equilibrium between the liquid and vapor for a volatile phase. So at any particular pressure and temperature, you're always going to have a particular vapor pressure dictated by that chemical potential. And that also means that the chemical potential of the liquid and the gas are the same. And we're going to take advantage of the fact that gases are much easier to deal with. So we're going to treat our vapor or our gas as an ideal gas. This is a good assumption. It's unlikely to be a real gas at the low pressures that you get in most volatile liquids. And then we're going to compare it to a standard state. So we have the chemical potential of the gas is compared to a standard state chemical potential of a gas. And then there's a ratio of the vapor pressure to the standard pressure. And we're going to capitalize on this and use these gas properties to explain liquids in mixtures. So if we had a binary liquid solution, so a mixture, where we have A and B mixed together, they're going to have vapor pressures above that contain both A and B. So we wanted to set up the same thing. Let's capitalize on the fact that the gas and liquid vapor or chemical potentials are the same because they're at equilibrium. And so our chemical potential in solution of A and B is once again related to some standard pressure and our vapor pressure. Now we're going to redefine, at least reset the terminology for a pure liquid, whereas if we removed all of B and just had A here, this would be the chemical potential. So we put a degrees sign for the pure liquid of A and B. And therefore we're just comparing, so this is just like we had on the last slide, but we've added a degrees sign to show that we're comparing the vapor pressure over a pure liquid versus this is the vapor pressure over a mixture. So now let's put them together. So let's apply kind of a chemical equation to mixing. So we have moles of A, moles of B purely, and then we have the sum of those moles in the solution. So then our delta G, or our thermodynamics of mixing, so whether we get spontaneity or not, is just the products of the chemical potentials minus the reactants. Okay, so if we just take all of our chemical potential equations we had from the previous page, we substitute in and then combine some terms. We get rid of all of the reference states because they all divide or subtract out, and we're left with the delta G of mixing is related to the number of moles and the ratio of the vapor pressure over the mixture compared to the vapor pressure over a pure solution. Now we divide through by the total number of moles and we get a partial molar delta G of mixing, and so we see we have this term. Now we're in terms of mole fraction, and we still have the vapor pressure ratio, so mole fraction of each. All right, so when we're mixing two liquids, we're going to define ideal solution behavior in terms of Raoult's law. And that is basically that the vapor pressure of component I above a mixture is just whatever that mole fraction is in the solution times the vapor pressure it would be at if it was a pure liquid. So if our vapor pressure was 50 bar and this is a half a mole, so it's a half and half, then you should have a 25 bar vapor pressure above the liquid. And so what this means is that ideal solutions will show vapor pressures versus mole fraction that are basically linear, with the slope related to the pure vapor pressure of the liquid. Okay, and what this means, and so I've drawn a crude diagram which shows they should be linear. These should be lines here where you would have, so depending on what the vapor pressure of each component is, 0 to 1 of a two component mixture, as you go as you add more and more of this component, it approaches, when it's pure liquid, it's the vapor pressure of the pure liquid. It's the vapor pressure of the pure liquid. Okay, and typically Raoult's law is actually not a bad approximation for a solvent in a very dilute solution. Okay, so when we're looking at these regions here, where we're very close to just a pure liquid, typically most liquids mixtures will, or a lot of mixtures will act or follow Raoult's law. Now, if we use this ideal solution behavior, then our delta G of mixing is just related to so we substitute this in for our vapor pressure, and remember it was P1 or Pi over Pi naught, so the Pi naughts cancel and we're left with it's just related to the mole fraction in the solution. So the delta G mixing is RT, the mole fraction of A natural log, and then this would just be, actually, if we had multiple components, it would be the sum, however many mole fractions that you have, however many components you have. Now, I did want to have a little parenthetical down here. When you see a mole fraction represented as Y, that's typically the mole fraction in the vapor. X refers to the mole fraction in the liquid. We're looking at the gas in order to explain mixing in the liquid. Okay, so that's ideal solution behavior. We've set that. Works in a very small range of mole fractions for most solutions. But what happens when we deviate from Raoult's law, or we deviate from ideal? So we're going to define a new quantity, activity. And activity is basically the effective mole fraction in this case. And so activity is this ratio that we had defined originally in our delta G mixing. Okay, so if the vapor pressure over the mixture over the pure vapor pressure, so it's just that ratio, is going to be the same thing as an activity coefficient. We're going to define an activity coefficient and the mole fraction in the solution. And so activity coefficient is our comparison to ideal. And we can rewrite our chemical potentials originally so that now our natural log of our activity instead of the mole fraction, or excuse me, the vapor pressure ratios, and we're left with a mole fraction and activity coefficient. If we have a two-component system, we end up having two parts. We have our familiar ideal part from the Raoult's law slide, so that's ideal component of mixing, and then we have a non-ideal component of mixing. So what does it mean in terms of the activity coefficient? If this activity coefficient is 1, it's an ideal solution behavior. This part drops out. Actually, the activity is the same as the mole fraction, and everything's great. It's all just following Raoult's law. But if the activity coefficient deviates from 1, so if it's greater than 1, let's say, what does that mean? That means, if we looked at this expression, so that means our solution, that solution is overrepresented in the vapor. If we were to look at that, this ratio, we have more here than we do here, than we're supposed to versus ideal. So it's overrepresented compared to an ideal mixture in vapor. And what does that mean? That means it's trying to escape the liquid. They don't like each other as much, the two solutions, if we're talking about a two-component system. If it's less than 1, it means it's less represented in the vapor than it would be in an ideal case. And so in that case, if you have two components, that means those two components like to be in solution together, and so there's not a lot of escaping into the liquid. So our activity coefficient is a measure of the non-ideal behavior and could be interpreted chemically. So until next time,